All right. So let's talk about things like conductors and insulators. These are the materials that we get charge from and how charge behaves differently in these materials, okay? So just to start out with, not a clicker question, but is this a good idea?
Yes.
Not a terrible idea.
Very good idea.
How do you think these people are still alive?
Yes.
Unfortunately, yes.
Yes, they are.
No, I don't know.
They have eternal life.
No. Well, without getting philosophical, they may or may not still be alive in some context.
They might have forgotten to plug it in.
Yeah, I mean, you don't know if this is plugged in. We can't see, but yeah, I think it's like a grill.
Yeah.
It's like a. I mean, how else are you gonna get hot dogs in the pool without getting out? All right, is it a George Foreman grill? That would be great. George, yes. Yeah. Oh, yeah. That was the point of this. The water is a conductor. Okay, that's why it's a bad idea. So water conducts electricity. And what is electricity? Why do we call it electricity? It comes from electrons, right? So electricity is made up of electrons. So when you're actually getting power from the wall, that's moving electrons. So when you move electrons, we call that electricity, and we harnessed it very nicely to do all kinds of stupid things like have tiny phones, and I can plug all this crap into my computer because thanks electricity, okay? We don't have to use the chalkboard as much. So the reason is you intuitively know that something about water, something about the material water is special, right? If you saw this not in water, if it's just on a table, it's not that scary, okay? I mean, it's not a great use of extension cords, but whatever. Yes?
Just a quick question. When it comes to like electricity and people getting shocked, since you guys are in the pool, does whatever that electric charge is coming from, does it have to be proportionate to the medium that it's in? Like whatever you drop in that water.
So what's tricky is if you're plugged into the wall, you kind of have an endless supply of electrons coming out of the wall. So it doesn't actually, I mean how fast it travels and all that stuff, yeah, that'll matter, but there's a scalability issue, right? Because if you're in the ocean and it gets struck by lightning a couple miles away, it dissipates before it gets to you. But that is lightning, of course, is a discrete quantity. There's only so much lightning and then it disperses. Whereas a power outlet is a little bit more dangerous. This is why you shouldn't charge your phone while in the bath, while looking at it, because it can actually kill you. If you don't have a charger that has an auto shut off, right? People have died dropping their stupid iPhone in the bath while it's plugged in. See, if it's not plugged in, right, it might hurt a little if it shorts out and shocks you, but you're not going to die. If it is plugged in, then it'll just keep shocking you, and you're dead. Okay? What? Yes.
Kind of like, have you ever seen that video of people holding a ton of people holding hands and they get tased?
Yeah.
It sucks.
Yeah.
It's
Because you're a conductor, right?
Yeah.
But the people farther away aren't going to feel it as much as the people close by, but it will conduct a certain amount of time. So yeah, it does dissipate as it gets farther out. But yeah, it depends on what your source is. Okay? So, conductors versus insulators. Conductors, metal, water, and why are you a conductor? We're made mostly of water, okay? And actually water with really pure water doesn't conduct as well as salt water conducts better because salt is an ion, so it's easier for electricity to travel through that water. So the kind of water matters. Anything you could stick in an electrical outlet that won't feel good, that's a conductor. Okay, I don't recommend trying that, but if you're on the fence, all right. Insulators, the charges are more fixed in place. So electrons are free to move around in a conductor. That's why the wires are made out of metal. Okay, wires are conductors. Insulators, not so much. So plastic is a good insulator. Glass is a pretty good insulator. Apparently yarn and rubber ducks are good insulators. Okay, so yes. Is water vapor conductive? Yes, but it's a little bit tricky because it's dispersed out, right? So it can conduct, but it can't necessarily jump from one water molecule to the other very easily. So steam. You're not going to get electrocuted by electrifying steam unless you have a lot of charge.
What about plasma?
Plasma is different because plasma means that plasma is a completely different state of matter where basically you either have the pressure heat set so that the material has completely come apart. So it's like there's a lot of electrons that are free, but it behaves differently. So there's a whole field of physics called plasma physics. But usually things have to be like really, really hot or some sort of special material. Okay. Over here we have like a spool of copper wire and a metal spoon. So most metals are conductors. Insulators are things like plastic and cloth and things where electrons aren't free to move around. Now what this looks like on a sort of microscopic scale is, let's say we have this sort of the nucleus with core electrons. So there's sort of the electrons that are tied into the nucleus of an atom. And then valence electrons are going to be represented by yellow. So both conductors and insulators have these nucleus with core electrons, but it's the valence electrons that really have a different role depending on whether you're talking about a conductor or an insulator. So for conductors, basically valence electrons can go anywhere in the metal or in the conductor. In an insulator, they're sort of fixed in these little zones right around the nucleus. So an electron over here can kind of go all over the place. An electron over here is stuck, just sort of wandering around the nucleus. So that's the general idea. So we call this space where electrons are free to move the sea of electrons. And remember, every piece of matter is made up of both electrons, protons, and neutrons to some extent. But what's interesting about the sea of electrons is the electrons move around a lot. And so we're just going to show the negative charges here, but you can assume that there are also positive charges, but the positive charges are more fixed in place. So let's say we bring a positive charge close to this, and you can see the electrons move towards the positive charge because they're attracted to it. What this doesn't show is that this side over here now has sort of a net positive charge because the whole thing, right, has positive charges fairly evenly distributed, and those don't really get to move around. But that once you move your electrons all over here, that means you're only left with positive charges over here. So that's what happens when we have a conductor. When we have an insulator, not so much, okay? And we'll talk about that in terms of dipoles. Now, in an isolated conductor, any excess charge is located on the surface. And the reason for that is, this is sort of a minimization problem. Think about sort of a middle school dance model where the people are electrons, and you sort of end up with a bunch of people around the edges of the wall. And that's because that's the maximum distance you can have away from the things that you're repelled by, okay? So if everybody hates each other and you put them in a round room, they're all going to go to the walls and be evenly spaced. And that's pretty much how conductors work, so how charge in a conductor works. If you have any charge in the middle, right, it's going to be repelled and pushed out to the walls. So, you can scale this to a three-dimensional model. If it's a sphere, then they're going to be evenly distributed around the sphere. And this is assuming there's no other charges interfering. So the electrons are free to move. They don't want to be near each other. And so the configuration they take by default is as far away from each other as possible. And that's just spread out along the wall because they can't go any further away from each other. So here we have an electroscope. You can make this yourself. It's actually pretty fun. But essentially what it is it's a conductor, right? So here up top you have this conductor, right? And it's connected through an insulator down to another conductor. There's two leaves down here. So both models, there's these two leaves that are free to move, essentially. At least one of them has to be free to move for this to work. And you can make one of your own here. It's a really fun thing to do at home. And you can use it to sort of test the electrical charge of things. But the key here is, because these are free to move, if you change the configuration of electrons by, say, bringing something charged near this, whether it's a positive charge
or, you know, something negatively charged up here, what happens is the electrons move around in the metal. They can move wherever they want, and they redistribute according to what works best for them. And then you can get different effects. So here's a clicker question. Try this out so to get the idea of what an electron is. So when a charged rod is brought near the electroscope without touching it, what do you think happens to the leaves? Okay, so what happens is initially they separate, but they move back when the rod is removed. And what's happening here is that if you have a charged rod, so let's say we have something with a negative charge, okay? That means that the negative charges that are here are repulsed by those negative charges, so you end up with them moving down to the leaves, right? So that means there's more positive charges up here and more negative charges down here. Well, if you have more negative charges down here, you're gonna end up with a repulsive force. The negative charges don't want to be by each other, and that means the leaves are going to end up sort of doing this. Okay, but once you move this rod away, all the stuff goes back to its normal configuration, and your leaves go back down. Okay. Here's another question. So here now we have a charged rod, but you actually bring it into contact with the electroscope. And so that means charges can jump back and forth between the electroscope and the rod. Okay, so in this case, if you bring the rod close to it, you have negative charges on the rod. But if you actually touch it to the rod, then this is going to end up with electric charges everywhere on your conductor, and they're going to evenly distribute because they want to be as far away from each other as possible. That means even after the rod's gone, you still have these charges here. And remember, when we have the charges here, that's going to make the leaves go like this. But because there's no way for the charges to leave now, it's going to stay up. And this will actually be a little bit less strong effect because now the whole thing is negatively charged, so they have to distribute themselves evenly. So the leaves probably won't go as high if you have the same charged rod, but they're also not going to go back until you discharge the rod. And honestly, the easiest way to discharge it is to just touch it because you are also a conductor, which is why you shouldn't be in a pool with electrical stuff. Okay, so the answer is going to be B. They separate when the rod is removed, and they stay separate. So charging by induction is what we've just talked about. So if you have an electroscope, touching things really is the way that you can charge by induction, okay? So if you're touching the electroscope with no contact, you can bring negative charges up, and then you can bring, if you touch this thing, you can have negative charges come to you. Once this thing is negatively charged, then this is what we just talked about, the leaves will push away. So if you can charge and discharge by contact, so if you have a charged rod and you touch it to a conductor, the charges will distribute onto the conductor. Discharging, if you have a conductor and you touch it to another conductor, then it will pull some of the charge, but not all of it, right? It always evenly distributes. So you can do this in phases where you basically take everything and distribute it over all the surface area multiple times, but you touching it, you're a pretty good conductor. You're touching the ground. If you don't have big, thick shoes, you're grounded, and charges can go into the ground as well.
Answer this question. All right. We're not sure. So please discuss and... So it's either positive or negative. Nobody thinks it's neutral anymore. All right. So here, let's draw this out. Here's our two spheres, okay? They're neutral. And here's this positively charged rod. So when you bring the positively charged rod near this, what happens to our neutral spheres?
They become hot.
Well, they're still neutral, but what happens to the charges in them?
They move.
They move. Which way do the positive charge, well, which way do the negative charges move?
Towards the positive.
Towards the positive. So we have these negative charges over here. This is more positive over here, okay? If we separate them before we take this rod away, right, that means this one's still going to have more positive charges, negative charges. This one's still going to have more positive charges. Then once we take the rod away, those things distribute, right, more evenly, but they're still there, okay? So as a net, these things are still neutral, but since we polarized them, since we made more charges move over here and then separated them, the charges can't jump back across when they redistribute. So this ends up still being more negative. This ends up still being more positive, even after we take the rod away. Okay? All right. Here is another one. Okay, we're mostly thinking C. Please discuss. We'll vote again. Much better. Okay, so it is going to be neutral. This time, right, you bring the positive charges here. You have negative charges that end up over here, but they don't move from sphere to sphere. So even when you pull these apart, they're still electrically neutral once they redistribute, okay? Let's talk about the Van de Graaff generator, all right? This is a Van de Graaff generator. Here's the diagram. So as you can see, this thing is metal, all right, that's a conductor. It's got this belt inside of it, okay? Inside this thing, attached to the metal, are these little brushes. It looks like a toothbrush, right? So there's a metal bar, it's got a little brush attached. This thing, the belt, goes past the brush, okay? So basically you've generated a friction-making machine. So instead of having to rub things together to get friction, now you have an automated system that just takes electrons off of this metal thing and then sends them to the ground, okay? So the longer you have this on, the more positively charged this thing gets, okay? So let's try, give me volunteer. All right. Yeah? Okay, just give me a second. Let me do a quick demo and then your turn. All right. How's your hair? Pretty short? Okay, that might be okay. Put the wig on if you want. All right. So, you can hear it's starting to like fire up. So this thing's starting to get more and more positively charged. Okay, this thing's connected to ground, so it doesn't shock me. It's a nice insulator. All right. So as you bring this closer, you can see this thing called dielectric breakdown. Can you guys see that? You can move closer if you want. See that little like blue lightning? Yeah, we can turn the light off. It's more exciting. Well, that light controls nothing. For the drama. Yeah. All right. Used to make the old projector flicker. This one must be better. You can actually feel it like pushing this thing. All right. All right. So, well, maybe we can actually buy one for the house. Oh man, that feels weird. All right, lights are back on-ish. That thing's building up. So, you can put some charge on this thing. You can see, like, look, you can see it actually moving this thing around. Alright, so now this thing has been painted with some charge. Oh, that thing's getting crazy. Alright, so we're going to do some experiments. So, any volunteers? Are you unvolunteering? Alright. Actually, I think let's try to figure out who has the best hair. Is your hair like gonna? Let's find out. Here, come. Otherwise, we'll have to put someone in a wig. All right. So I'm gonna have you stand on this platform.
All right.
All right. Why is he standing on the platform? He's not grounded, so that means he will store charge instead of dissipating it into the air. Okay, so touch the ball.
All right.
Yeah. So we're gonna turn this on. Okay. And we're gonna see if what it does to your hair. You're not wearing any like electronics, right?
For the most part, no.
Okay. So you see his hair starting to sort of stand up. You gotta get like, yeah. If you get close, you can see it.
I feel a lot of static on my clothes.
Yeah. Okay. You can step away from. You can let go and step away. It won't shock you maybe through your foot. So let go.
All right.
Oh, sorry.
No worries.
All right. Now you can step down. And you can go.
Oh.
Did it hit your foot?
No, it got me on my nose.
Oh.
Yeah, that's why.
Okay. You okay?
Yeah.
All right. So did you guys see his hair?
Yeah.
It looks sort of like, well, you can put the wig on this thing. We actually like recently made this, like changed the brushes on this thing, and it works much better now. So generally, what this is supposed to look like, we can put this directly on this thing.
It's just dangerous.
It's that, right? But you have to have pretty light hair and not discharge at all. All right. So what's happening here? Why is it doing this? Yes.
Plug up on the wrong
So
side of
the
bed.
metal thing is it's positively charged. So now this is positively charged too because we charged it earlier. See, it's repelling it. Okay, so the metal thing gets positively charged. It ends up on the hair, and when all your hairs are positively charged, they repel. Okay, we can actually uncharge it a little bit by sending it to ground. All right, so this is a good way to have a bad hair day. All right, you can also move the charge over here. So like. Oh, it's getting bad. That's pretty charged. We can charge this thing up over here. Okay, so now this thing has a positive charge. This thing's going great today. Alright, we're gonna do one more experiment before It's not that bad. It's just I've done it a lot now, and it's like starting to. No, it just. It's like you think it doesn't. It's one of those things you just don't get used to. Like some things when you just get used to by doing them a lot. This one every time it happens is just as upsetting as the last
Usually
time.
burns. Electricity.
It's enjoyable, right? Getting shocked. It's a different feeling than when you like lick a 9-volt battery or you get electrocuted by an outlet, because when you get electrocuted by an outlet, it's like it's kind of a humming sensation because it's an AC current.
Yeah.
I've been electrocuted by lots of things.
Oh, me too.
When I was in undergrad, I worked in a laser lab, and my laser broke, and I had to replace this part in the laser. So I was like under this table for like a week, replacing these parts in the laser. And one of the grads, I didn't really know what I was doing, but I was like, I have an electrical schematic, and I've taken 1 semester of electrical classes, so I can totally do this. I took upper division circuits, and I was like, I know everything about electricity now. And they came in, they're like, you guys, you know that, did you make sure you discharge the capacitors? Because all of the capacitors in here can kill you. And I was like, no, I just didn't touch them. All right, so we're going to do a little experiment. So I'm going to ask you guys what you think is going to happen. This is a metal tray. It's got styrofoam popcorn in it. Okay? What do you think is going to happen when we turn this guy on? Yeah, popcorn. Why?
That's positive charge.
Yeah, it's all going to be positively charged. This thing just sucks electrons off stuff. So here we go.
One. That's all we get.
Yeah, give it a minute. Put more popcorn. Sometimes this is more dramatic than others. I think I should put more popcorn in there. And then I have to pick it up. Okay, well, let's try again. Well, alright, that's good enough. You guys are right. Okay.
The projector didn't flicker, but the TV screen did.
Yeah. Those are older.
You know, you can pull it off with people as well. Here, I pulled off this trick one time by making kids believe I was a magician. What I did was I rubbed my butt on a bunch of bleach or soap. What happened was I slipped this wrapper in my hand, and the wrapper started floating. And every time I put my hand under it, I kept it up in the air, and I'm wondering how I was doing that.
Because you're a wizard.
No.
A physics wizard.
Same thing as that.
Yeah, I know. Just kidding. But that's awesome. All right. So do we got from this, okay? So remember, oh, and we charged, let's see if that thing's still charged. We can test it. I think it should still be charged. It's not that humid today. Yeah. You put some charge on here earlier? Still charged. What else is probably still charged? Charged here. All right. So the electroscope is a good way to detect charge. The main thing is, though, this thing can't tell you if it's positive charge or negative charge, right? It can just tell you if there is charge. So, all right. So remember, we have insulators. Those are materials whose charges are not free to move around. And then we have charging by friction. But of course, there's lots of different outcomes for charging by friction. And in the next lab, we'll spend some time talking about that. Okay, remember, charges are actually physically ripped off. So remember, for glass and silk, right? You rub those together, it turns out the glass ends up positively charged and the silk ends up negatively charged. For wool and amber or fur and plastic, you get just the opposite, right? The thing you rub, the fur or wool, ends up positively charged and the plastic ends up negatively charged. So how do we decide which one's going to be positive and which one's going to be negative? Yes? Not quite. Any thoughts? What determines that? Yes? So not quite. It does depend on the material. Yeah.
Well, I know glass is polymer, so the way that the molecules work with the material.
Yeah, so it depends on the two materials and their molecules, right? And it actually turns out, without knowing too much about the molecular makeup of things, there's a scale you can look at. You don't need to memorize this, I just think it's interesting, and it'll be more interesting when we talk about the lab, but this is called the triboelectric series. Okay, if you're interested in this, it's from a cool book called Nature's Electricity by Charles Adams. Okay, it sounds kind of like a yoga manual, but this is the scale. So these are very positive things. These are very negative things. So remember when we talked about how when you rub fur and amber together, right? One of them ends up positively charged, one of them ends up negatively charged. You can tell the fur is going to end up positively charged because it's on the more positive side of the scale. The amber or plastic is going to end up negatively charged because it's on the more negative side of the scale. So the relative distance of things tells you how much charge you're going to get, and the position of them with respect to the thing you're rubbing it against tells you whether it's going to be positive or negative. Okay, so all materials have these capabilities because they're all made up of molecules. Some are better than others. You can see the ones in the middle don't work as well as the ones near the end, and so on and so forth. Okay, but really the main thing is how far apart these are. So glass and silk doesn't work nearly as well as fur and plastic, which is way over here. So you can see these are really far apart, right? So they're going to give you a really strong effect. These are pretty close together, so they'll give you a much weaker effect. Yes?
Where's some color?
These are the pairs that we had already talked about. So glass and silk, that's a pair. Wool and polyurethane, that's a pair. And fur and amber, that's the cat, right? So, okay. Yes?
So, why do we use copper for copper wire?
So this is different. We're just talking about static charge. And what do we mean when we say static in physics? It's not moving, right? So we've been talking a little bit about electricity. But electricity is a little bit different, right? It's a moving charge. This is not talking about how we want to move charge around or even how we want to store it. It's just talking about how we generate charge with friction. So this is a very special subset of what we're talking about. Okay.
Yeah.
Yeah, I mean, you can rub things against metal and generate a charge, but it's going to distribute differently on the metal after. So, yeah, the main reason we use copper is it's a good conductor. Yeah. It's actually a good heat conductor and a good electrical conductor. Metals are nice that way, but for electricity, I mean, gold actually conducts a lot better. Why don't we use gold wiring? It's expensive, yeah. Yes. Rabbit fur and regular fur?
Yeah, so like second to the left is rabbit fur.
Oh. Rabbit fur? Well, actually, you could probably break it down even more by animal because different furs have different molecular structure. So rabbit fur just happens to be one we use a lot because it's especially good at generating electric charge. That's the word.
There we go.
Okay. Whew. All right. Why does this happen? Let's imagine you just did your laundry. Why do you get static after taking things out of the dryer? Yeah, it moves. What does that do? Friction, right? Your clothes are rubbing together, right? And your clothes are not all made of the same material, so when they rub together, some of them are going to end up more positive and some are going to end up more negative. But of course, what is the dryer drum made out of? Metal. So it's a conductor. So any negative charges that are loosened, right, that can come off, those are more likely to leave. So your laundry, it usually ends up sort of net positively charged, but it's also got positive and negative charges. Okay? So why does this help? What does it add back? More negative charge and scent, but that doesn't help with the static. That's just a bonus. So you don't have static and you smell nice. Yeah. So yeah, it adds back some of the charge that you lose when charge is ripped off and goes out through the dryer. Okay. All right. And of course, when we talk about electricity, your dryer, the metal casing, the metal drum, those are all grounded. Why? So you don't get shocked, right? And we'll talk about why 3-prong plugs are better than 2-prong plugs at making sure you don't get electrocuted. Yes?
Is that why when you pull the lint out of the lint trap, you don't get shocked from it?
Huh. I don't know. I've never thought about that.
That lint thing's plastic.
Yeah, but I mean, that could hold charge. I will think about that. The other thing is if you take your clothes out and they're still a little bit damp, do you ever have static then? No, right? So if it's the water, right, it's the heat and the dryness that allows the charge to stay. If things are wet or if it's humid or if it's not as warm, then you don't get as much static shock. So the time you normally get shocked by like your car or a door outside is when it's pretty cold and pretty dry. Okay? Okay. Huh. Let's talk. We're gonna skip that one. All right. So let's talk about electric dipoles. Okay. So I want you guys to think about a situation. So have you ever rubbed a balloon on your head and then stuck it to the wall?
Yes.
Okay. So what happens when you rub the balloon on your head? Yeah. So let's say the balloon. Well, we can go back and figure out which one it is. So balloon and what are balloons made of? Latex on there? It's probably something like these plastics. Okay. So human hair is over here on the positive side. Okay. And latex is on the negative side. So you can assume the balloon ends up negatively charged. Okay. So if our balloon ends up negatively charged, the wall is neutral, right? Why does it stick to the wall?
So it says charge in the wall. So whatever charge the balloon is, it's going to attract the opposite from the wall.
Yes, but why, if the wall's a conductor, why can it still get some of that charge to move? Okay, so let's talk about that. It's because of dipoles, Okay? Dipoles are usually what insulators are essentially made up of, because even though the electrons can't move wherever they want in an insulator, they can shift around. Okay? So a dipole is when you have a positive and negative charge stuck together. Okay? But it can wiggle or rotate or sort of shift. All right? So here's our positive and negative charge. So for instance, if we put a positive charge here, a dipole can't move from place to place. Hi. Physics 200. A dipole can rotate so the negative charge gets close to the positive charge. And then if you have one like this, right, you can have it rotate so the positive charge ends up close to the negative charge. So if you have a whole wall made up of dipoles, okay, you can bring a charge over here, like the balloon, and you end up getting this sort of effect. Okay? And they don't move a lot, but they don't need to move a lot, right? You just need enough force to prevent what? What force are you trying to cancel out for the balloon? Gravity, right? And how much does a balloon weigh? Not much, right? So you don't have a very large force you need to cancel. You just need a little bit. So because gravity is pretty weak for a balloon, right? You just need a little bit of charge, a little bit of change in structure of the electrical stuff in your wall in order to get it to stick. Okay, and it doesn't last long, right? Because as soon as the charge starts dissipating, it falls. But that's why you can do that with a balloon, even though the wall is an insulator. If the wall was metal, would it be easier or harder? Easier, because you could get a lot more charge, a lot more positive charge, like all this positive charge would move over here. It'd be much closer, okay? And then it would be easier to have things happen. So I want you guys to think about one more thing, okay? So here, notice as I bring this closer, if it's over here, this leaf isn't up very high. As it gets closer, it's much more pronounced, right? So there's some relationship with the distance and the force that this thing feels, right? So let's talk about some actual math, because we've done no real math yet. And as you know, there is no real physics without real